Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good day to whom is may concern. I do hope that you and your family had a wonderful, happy and healthy day every day. May Allah bless you in the best of iman and taqwa, inshallah. Welcome to all of you to this video. My name is Idris Saad. This video is made for my lecture on the subject of MEC451 Thermodynamics. Please note that this video is best viewed with reference to the lecture note that I have provided earlier to all of my students. Also, please note that this subject is specifically for UITM student for the program of EM220 Bachelor of Engineering Honors Mechanical and EM221 Bachelor of Mechanical Engineering Manufacturing Honors. Nonetheless, I do welcome anyone who would like to watch this video to learn something about the thermodynamic that could benefit your general knowledge. This is video for the lecture of chapter 1, the introduction and fundamental concept of thermodynamics. Basically, this is video for part 1 for chapter 1. In this part 1, I will cover only the introduction to the thermodynamic and the law of thermodynamics, which consists of the zero law, the first law, the second law, and the third law. Okay, now let us proceed to the next content. In this chapter 1, the introduction and fundamental concept of thermodynamics, we will learn 6 main topics. As listed in this slide, they are the introduction to thermodynamics itself, the law of thermodynamics, which are the zero law, the first law, the second law, and the third law of thermodynamics. Next, we will learn about the thermodynamic system. The thermodynamic system is consists of the type of the system, the thermodynamic properties, the thermodynamic state, thermodynamic process, and also the thermodynamic equilibrium. After that, we are also required to study about the thermodynamic processes and thermodynamic cycle. This chapter also will cover a little bit about the temperature scale, the pressure, also the device used to measure the pressure, which are manometer, barometer, and the atmospheric pressure. Finally, this chapter should be concluded by studying about the energy, the environment, and also the sustainability issues. That's all for this chapter. However, as I mentioned earlier, this video is only covered the first 2 topics on this chapter, which are the introduction and law of thermodynamics. Okay, let us carry on to the next slide. Okay, as the first time study about the thermodynamics, let us start this topic by exploring the meaning of the thermodynamic. In general, thermodynamic is just a sign of the relationship between the heat, the work, the temperature, and also the energy. In broad term, thermodynamic will deal with the transfer of energy, which is basically in the form of the heat from one place to another and from one form to another form. In simple definition, the thermodynamic is basically a study about how heat is converted into the useful work, or it is simply converting heat into work, or vice versa, which is also the study about converting work into heat. The example of converting heat into work is the engine of the car as shown on this figure aside. As we can see on that figure, we have to put the petrol fuel into our fuel tank, as it actually the chemical energy that is stored in the form of the fuel. After that, the fuel is being transferred into the engine. In the engine, the fuel is burned through the combustion process, and the chemical energy that is originally stored in the form of the fuel is converted into the heat energy in the form of fire. After that, part of this energy is converted into the work energy in the form of moving car. Finally, part of that heat will be disposed in the atmosphere as a waste. Based on this example, we can learn that in order to move a car, we need the energy being transferred from chemical to heat and also to work. These energies are also being transferred in the form of fuel, fire, and moving car respectively. This is how we are converting heat into work. That is what is meant by the thermodynamic is dealing with the transfer of energy that consists of heat energy from one place to another and from one form to another form. In this slide, the animation of the typical auto air conditioning system is illustrated on how we are going to convert work into heat. For the explanation purposes, please imagine your split unit air conditioning system that have indoor and outdoor unit. As we all know how to use the air conditioning unit, the first we need to turn on the electrical switch. Basically, when we turn on the electrical switch, we are actually giving the electrical energy to the system. Then, when the electrical energy was given to the system, the compressor will do a work. From that, the refrigeration gas will move inside the system. As you can see on this animation, the red area will have high temperature space as per your outdoor unit of air conditioning system, and the blue area will have low temperature space as your indoor unit of the air conditioning system. Based on that, the energy is being transferred from electrical energy into work. And finally, we have heat energy in the form of cool and hot spaces area. That is how we are converting the work into heat. Again, it is a mesh with the definition of the thermodynamic as I explained earlier. As an alternative definition, the thermodynamic is the science of energy that is concerned with the way energy is stored and transferred within a body. In both examples, for a car, the energy is stored in the form of fuel, and for the air conditioning unit, the energy is stored in the form of electric. then they are transferred to the other form of energy, but it must involve the heat energy in order to fulfill the definition of thermodynamic. As a conclusion, the energy must be transferred, otherwise it is no give us any benefit. In general, there are three types of energy transformation. The first one is in the form of heat, the second one is in the form of work, and the third one is in the form of mass flow. From these three types of energy transformation, the heat and work are mutually interchangeable. What is mean here is we always change heat into work or work into heat in the thermodynamic system. Basically, there are many examples of the application of the thermodynamic. Note that thermodynamic is the system that convert energy which involve heat energy. Popular application of the thermodynamic system are the reciprocating engine that being used for the automotive engine, the steam engine that we use it for the steam power plant, gas turbine engine that we use it for the aeroplane engine, and also the gas turbine power plant. Okay, note that refrigerant, we use it in the air conditioning and refrigerator system, and heat pump is used for the heater or dryer unit. The diagram on the left hand side is illustrate the schematic diagram for the thermodynamic process to convert heat into work, and the figure on the right hand side is the schematic diagram of the thermodynamic process that convert work into heat. Okay, now I will explain to you about the form of energy. By definition, the energy is just the ability to cause changes. In physics, energy is the quantitative property that must be transferred to an object in order to perform a work on or to heat up the object. Quantitative mean a physical quantity of a property of a material or system that can be quantified by measurement. A physical quantity can be expressed as the combination of a numerical value and a unit. For an example, the physical quantity of the mass can be quantified as n kilogram, or we may say as 5 kilogram, where n or 5 is the numerical value and kilogram is the unit. A physical quantity possesses at least two characteristics in common. One is numerical magnitude and the other is the unit in which it is measured. So that is meant by quantitative. Okay, now we move back to the energy. Basically, the energy is invisible, or it is existing in the form of abstract. What is meant here is we could not see the energy by using our naked eye. Energy does not exist in the physical form as table, chair, and other things that we cannot see with our naked eye. The energy must exist in other physical substance. The analogy that I always use to describe the energy and substance is in our soul and body. The soul is basically is analogy as the energy, and the body is analogy as our substance. We could not see our soul, but we can see our body. Without a soul, the body could not move. So that is the simple analogy about the energy and the substance. As for the energy, the heat is the energy and the fire is the substance. If we can see the fire, then we should know that the heat energy is there. Similarly, the object is the substance. When the object is moving, then we know that the energy in the form of work that cause the object to move. Also, when we see the water of any fluid is moving, then the water of the fluid is the substance. So, what caused the water to move is the energy in the form of mass flow. That is how we know our energy. So the energy is basically can exist in numerous forms such as thermal or heat or kinetic, potential, electric, magnetic, chemical, including nuclear, and their sum constitute the total energy of the system. The total energy is normally denoted as capital E. The energy is actually can be divided into two main groups. The first one is we call it the microscopic energy, and the second one we call it as the macroscopic energy. The microscopic energy is defined as the form of energy associated with the molecular structure of a system and the degree of the molecular activity, and they are independent of outside reference frame. Based on language, micro means something small. In order to understand the microscopic energy, we need to refer to the figure of atom and molecule on this slide. As we learn in the chemistry, the molecule are made of atom. In atom, we have proton, electron, and neutron. The movement of electron will produce the electrical and magnetic energy on the molecule. So now, the molecule has magnetic and potential energy. Also, the molecule has its own mass. Based on physics, the mass is always reacting with the gravity, and when it has different height from its datum, then the molecule will have the potential energy. Also, if the molecule is moved, it will have the velocity. As we also learn from physics, any mass that react with the velocity will produce the kinetic energy. So, as a summary, in an individual molecule, we will have at least four forms of energy that are electric, magnetic, potential, and kinetic energy. These energies that possessed by an individual molecule is known as the microscopic energy. Imagine that in one bottle of water, there are millions of molecules. Thus, each individual's molecules in that water have this type of energy or have this form of energy. Therefore, the sum of all microscopic of energy is called the internal energy of a system, and it is denoted as capital U in the unit of kilojoule. That is the microscopic energy. Okay, now let us look at the macroscopic of energy. In contrast with the micro, from language point of view, macro means something big or in bulk. By definition, the macroscopic energy is the form of energy that a system possesses as a whole with respect to some outside reference frame such as kinetic and potential energies. In other words, the macroscopic energy is the energy of the whole substance. Remember that the energy is exists inside the substance. So we have to understand also about the substance. For an example, consider a liter of water, or we call it 1 liter of water. If we consider the energy within the molecule of the water, that energy become the microscopic energy. However, when we consider the energy within the whole 1 liter of water, it will become the macroscopic energy. So that is the macroscopic energy, and it differences between the microscopic energy. As a review, the kinetic energy is the energy that a system possesses as a result of its motion relative to some reference frame. That means any mass which has a velocity will have the kinetic energy. So the kinetic energy is always denoted in thermodynamics as Ke. Mathematically, kinetic energy is calculated as half mv power of 2. For the potential energy, that is denoted as capital PE for the subject of MEC451. It is basically the energy that a system possesses as a result of its elevation in a gravitational field. It means any mass will be attracted to the gravity, and if there is a different height from its datum, then it must have the potential energy. Recall that the equation for the potential energy is mass times gravity times the different height. So that is all about the form of energy. The figure on the left hand side is illustrate the difference between the macroscopic energy and microscopic energy. As I explained earlier, the microscopic energy is the energy that possessed by the molecule in the substance. As you can see on that figure, the movement of the molecules is a result from the microscopic energy, which are the kinetic, the potential, the electric, and magnetic energy of the molecule. And the sum of all microscopic energy is known as an internal energy. The microscopic energy is normally calculated by the chemical engineer. As for us, the mechanical engineer, we are more interested in the macroscopic energy. As you can see on that figure as well, the macroscopic energy will move the disk inside the cylinder. In thermodynamic, in thermodynamic, we call that this as a piston. Obviously, we can calculate the velocity and different height of the piston after it moves. Eventually, we can measure the kinetic and potential energy as the macroscopic energy. That is the difference between macroscopic and microscopic energies. The figure on the right hand side of this slide is also illustrate another example of the difference between macroscopic and microscopic energy. So, the energy inside the engine of that motorcycle can be considered as the microscopic energy, and the sum of it is the internal energy. From that energy, it will move the motorcycle to climb up the hill so that the motorcycle have the kinetic and potential energy. Based on that, we can form an equation of the total energy in the system as the internal energy plus kinetic energy plus potential energy as written in this slide here. So you can see here, so this is internal total energy. This is equal to internal energy, kinetic energy, and potential energy. Okay, also please note that thermodynamic deals only with the change in total energy of the system. What it means here is we will calculate the different energy before and after the process. That is more important than only calculate the energy at the before process or after the process. As a conclusion, the total energy is the sum of energy inside the molecule, which is the internal energy, and within the system, which are kinetic and potential energy. So that the total energy of the system is equal to internal energy plus kinetic energy plus potential energy. Okay, on this slide, I will explain about the concept of energy from the thermodynamic point of view. As we learned in the previous slide, the energy can be divided into group of microscopic and macroscopic of energy. For the microscopic energy, we usually use it as the storage of energy. Let us consider the petrol fuel as an example. The petrol fuel is existing in the form of liquid. Of course, it made from the fuel molecule. Inside the molecule, it has its own kinetic, potential, magnetic, and electrical energy that we sum it as the internal energy. That's what is called as the energy in store. That means the fuel is keeping the energy inside it before it is transferred into another form. As for the macroscopic energy, we consider it as the energy in transit. As we learned in the previous slide, there are two types of macroscopic energy. One is kinetic and the other one is potential energy. Both kinetic and potential energy is needed to move. Without moving, we don't have the velocity and different height. So we need the microscopic energy to store our energy, and we need microscopic energy to move our energy. That is then fulfill the definition of thermodynamic, which is transfer of energy, which involve heat energy from one place to another and from one form to another. In thermodynamics, we have three ways to transfer the energy. Number one is by using heat. Number two is by using work. And number three is by using the mass flow. As you can see in this slide, we can move the piston by using mass flow of water that is pumping into the piston cylinder device. Also, we can heat up the pot by using the heat when we fire up the pot. In the case of work transfer, it can be further breakdown into mechanical and non-mechanical form of work. They are the pedal wheel work, piston cylinder device, and also the spring work that is fall under the mechanical form of work transfer, and the electrical work in the form of non-mechanical form of work transfer. Basically, this slide is explaining about the thermodynamic concept of the energy based on the microscopic and macroscopic energy. Now, we have finished study about the energy. I really do hope that you understand the energy from its meaning, form, group, and its concept. Okay, now let us move on to the law of thermodynamics. What is meant by the law of thermodynamics? Basically, the law of thermodynamics will define the fundamental physical quantities, which are temperature, energy, and also entropy, that characterize thermodynamic system. Note that a physical quantity can be expressed as the combination of a numerical value and a unit. Also, the thermodynamic law describes how these quantities behave under various circumstances and forbid certain phenomena during transfer of energy. What it means here is there are certain things that thermodynamic can do, as well as there are certain things that the thermodynamic system could not do or impossible to achieve. The thermodynamic law are describing some of the fundamental truths of thermodynamics that being observed in our universe. In general, the thermodynamic law are based on the nature of our universe. Scientists have listed 4 laws of thermodynamics. They are called number 1, the zero law of thermodynamics. Number 2, the first law of thermodynamics. Number 3, the second law of thermodynamics. And finally, number 4 is the third law of thermodynamics. Actually, it's quite funny that the law of thermodynamics start with the zero law. However, based on history, the scientist is first discovered the first law, then the second law. After that, they realized that there is something is needed to be addressed before the first law. That's why they name it as the zero law. So, as per studying this subject, we will follow the sequence from zero to fourth law of thermodynamics to make it simple as possible. As you can see on this slide, I have provided you a figure of the process of boiling water. Actually, on this process, all of the 4 laws of thermodynamics are involved. Okay, let us discover them one by one. Okay, let us start study the law of thermodynamics with the zero law. Okay, the zero law of thermodynamics is used to define the concept of temperature. So, it is very important to us as a mechanical engineer. Anyhow, thermodynamics is about transferring the energy from one form to another form that involve the heat energy. We know that the heat energy is exists in the form of abstract. That means we could not see with our naked eye. So we could not measure it. However, the heat energy must exist in the substance, which is the fire. Therefore, we can measure the temperature of the fire. That's why the zero law is very important for us as a mechanical engineer, particularly in the subject of thermodynamics. Okay, by definition that have been provided by the scientists, the statement of zero law is if two systems are each in thermal equilibrium with a third, they are also in thermal equilibrium with each other. Okay, in order to understand this statement, let us consider the diagram provided in this slide. As you can see on that figure, there are 2 cups of beaker on the left and right hand side respectively. That beaker will fill with the water and the fire is underneath both of the cup of beakers. Also, there is 1 column of mercury at the middle of the figure. Now, let us imagine that the water in both cup of beaker were at boiling condition. If we place the column of mercury in the boiling water at beaker A, the mercury would rise and stop at certain point. Then we can mark that point. After that, if we place the same column of mercury in the boiling water at beaker B, the mercury would also rise and stop at very similar point as beaker A. As a conclusion, since both water in beaker A and beaker B have similar level of mercury, then we can say that they are in thermal equilibrium even though they are in the separate system. That is what is meant by the statement of the zeroth law. Another observation is if we put the column of mercury in the freezing water at room temperature and pressure, we will get one stable point. After that, when we heat up the water until it's boiling, then it will stop at one stable point or another stable point. Interestingly, the distance of the mercury between the freezing and the boiling water is always consistent, or it always similar, no matter how many times we repeat this experiment, so that we always can calibrate that column of mercury. That column of mercury is known nowadays as thermometer. So the zero law is producing the thermometer to measure the temperature of any substances. As for calibration, there are several scientists who made a scale on that column of mercury. The Celsius thermometer have the reference point fixed at the freezing with the value of 0 and boiling point of value of 100 for the pure water. However, the Kelvin scale have reference point fixed at no temperature with the value of 0 and at freezing point of 273.15. However, the scale are similar for both Kelvin and degree Celsius. In simple words, temperature is just the degree of hotness or coolness of a body or environment, so that the column of mercury only measures the temperature of the body or the environment, not the heat energy. However, in thermodynamic term, temperature is a measure of the average kinetic energy in the macroscopic form of the particle in a sample of matter, which is expressed in terms of unit or degree designated on a standard scale. For our study, we will focus on two units only, which are degree Celsius and degree Kelvin. In general, all temperature scales are based on some easily reproducible state, such as the freezing and boiling point of a pure water, or we call it as the ice point and the steam point of a pure water. The ice point is a mixture of ice and water that is in equilibrium with air saturated with vapor at 1 atmospheric pressure, and for the degree Celsius is denoted as 0 degree Celsius, and for Kelvin is denoted as 273.15 Kelvin. The boiling point, or it also called as the steam point, is a mixture of liquid and water, and also water vapor without air inside it, in equilibrium at 1 atmospheric pressure. At the boiling point for the degree Celsius, so is write down or denoted as 100 degrees Celsius, or for the Kelvin it is 373.15 Kelvin. The rest of the unit, such as Fahrenheit and Rankine, you may refer to other source of information. In this slide, we can see the comparison of temperature scale between Kelvin, degree Celsius, Rankine, and Fahrenheit. As you compare the scale of magnitude between the degree Celsius and Kelvin, they are actually similar. What is mean here is 1 unit of degree Celsius is similar to 1 unit of Kelvin. The difference between degree Celsius is the reference point only. If we do a calculation, 250 degrees Celsius is not equal to, or it is not the same as 250 Kelvin. But when 250 degrees Celsius minus 100 degrees Celsius, we will get the result of 50 degrees Celsius. Also, when 250 degree Kelvin minus 100 degree Kelvin, we will get 50 degree Kelvin. The result of 50 degree Celsius and 50 degree Kelvin are similar. Since after minus, we get the different magnitude value. That what is mean by similar scale of the magnitude. Basically, all scale is similar as you can see on this slide. The difference is only the reference point. Some use what we call the ice point, some use the boiling point, some use the situation or the position where there is no energy at all. So that's all for the zero law of thermodynamics. Okay, now we shall move on to the first law of thermodynamics. In general, the first law of thermodynamics is another version of the law of conservation of energy, which is adapted for the thermodynamic system. The law of conservation of energy states that the total energy of an isolated system must constant, where energy can be transformed from one form to another but can neither be created nor destroyed. What is mean in here is we could not add energy to this universe, and we also cannot destroy the energy in this universe. The total energy in this universe must remain constant. What we can do is just transform it from one to another. Based on that understanding, we can form a mathematical model which is energy that enter into the system minus energy that leaving the system must equal to the change of energy in the system. In mathematical form, we can write it as E in minus E out is equal to delta E of the system. In a simple explanation, if you have 10 ringgit in your pocket and you buy a food for 8 ringgit, then the balance you have is 2 ringgit. Now, the question is your money is losing its value in this transaction? The answer is no. It is because the value of your money is changing from the unit of ringgit to the food. So you still have the value of 10 ringgit, which are the food and the balance of 2 ringgit. So that's what we call conservation of energy principle. Okay, now let us refer to the second figure in this slide for another example. At the top of the cliff, the potential energy of the stone is 10 unit and the kinetic energy of the stone is 0. Hence, the total energy, the potential plus the kinetic energy is 10 units. When the stone is falling down from the cliff, the potential energy is reduced. It is because the reduction of the height from the sea level, which is the datum to calculate the potential energy. However, the kinetic energy is increased due to the increase of the velocity of the stone when it falls down from the cliff, so that at any time the total energy is remain the same, but the energy can change from its form and magnitude. That's what is meant by the conservation of energy principle that govern the first law of thermodynamics. So that I hope you understand clearly the concept of conservation of energy principle and its mathematical model to form the first law of thermodynamics. In this slide, I will explain about the second law of thermodynamics. Please refer to the diagram provided in this slide. Based on that diagram, if we connect the hot fluid and the cool fluid together, we can observe that the hot fluid will eventually cool down and the cool fluid will eventually heat up until both of them will reach the thermal equilibrium. Based on that experiment, we can see three different phenomena, and we also can make three main conclusions. The first phenomena are, no matter how many times we repeat this experiment, the hot fluid will eventually cool down and the cool fluid will eventually heat up until both of them will reach the thermal equilibrium. Is never going to have the opposite phenomenon where the hot fluid become hotter and the cool fluid become colder, so that we can make the first conclusion, that is, heat is always flow from a substance at a higher temperature to a substance at a lower degree of temperature and does not flow in the opposite direction. For this conclusion, we are actually identifying the direction of the thermodynamic processes. What it means here is heat must always move from higher degree of energy to a lower degree of energy by nature thermodynamic processes. So that is the first phenomena. As for the second phenomena, if we change the type of the fluid, let's say the first one, we use water. After that, we change the water with the cooking oil. Then we change the cooking oil with the mercury and so on. Then what we'll have is there are a significant change in time for the substance to reach equilibrium temperature, as well as significant degree of equilibrium temperature with different type of substance that we use. Based on that, the conclusion that we can make is different substances will carry different amount of energy. So it asserts that the energy has its own quality as well as quantity in different substances. In simple words, for a different substance, it can only have certain magnitude of energy. For an example, in 1 kilogram of petrol fuel, we can only have approximately 43 megajoule of energy, while in 1 kilogram of firewood, we only will have approximately 20 megajoule of energy. That what is mean by it assert that the energy has its own quality as well as quantity in different substances. Okay, now we move on to the third phenomena. The third phenomena are if we place the thermometer at different places along the experiment apparatus as shown on that diagram, where that diagram showing that three places that have been measured its temperature. One is at the hot point, the second one is at the cool point, and the third one is between hot and cool point. We know that the heat is flowing from high to low degree of energy as in our first phenomena. That means these three locations, the magnitude of energy is different. In example, from high to low. When we put the thermometer at these three locations, we definitely will have different reading of temperature which are also from high to low, so that we can make a conclusion as different quality of heat will carry different value of temperature. Also, from the second phenomena, we learn that different substance will have different time and magnitude of the equilibrium condition. From this condition, the scientists have defined the new properties in thermodynamic study that is called the entropy, and it is denoted as S. The entropy actually is given as the change of the heat to achieve the equilibrium temperature. Mathematically, entropy S is equal to del Q over T, or the change of the heat over the equilibrium temperature. In order to understand the entropy, let us imagine that we mix hot water at 100 degrees Celsius and cool water at 25 degrees Celsius. Eventually, after mixing process, they are both will reach an equilibrium temperature, let's say at 52 degrees Celsius. Note that this is not the exact value. It is just an example. The question is, how much heat energy is needed to exchange to lower down the temperature of the hot water, and how much the heat energy is needed to exchange the cool water to increase the temperature with the surrounding. The answer for this question is the entropy. In simple words, the entropy is a measure of the amount of energy which is unavailable to do a work during thermodynamic process. I repeat, the amount of energy which is unavailable to do the work during thermodynamic process, or the energy that could not do a work. Why it is unavailable to do a work? It is because that energy is used to reach and maintain the equilibrium temperature. In a natural thermodynamic process, the sum of the entropy of the interacting thermodynamic system are always increased. That means entropy is not a conserved property like energy. For energy, we can change it, but the entropy will just be kept increased from time to time and from process to processes. So, as a conclusion for the second law of thermodynamics, there are three important usage. Number one is to identify the direction of the heat flow by nature. Number two, energy has its own quality as well as quantity. And number 3, to define the entropy of any thermodynamic system. So this is about the second law of thermodynamics. Okay, now we move on to the final law in thermodynamics, which is the third law. The third law states that the entropy of a substance that exists in the most perfect form of crystal is zero when the temperature of the crystal is equal to absolute zero, which is 0 Kelvin. Okay, before we can understand this, we need to recall the meaning of entropy in the second law of thermodynamics. The entropy is actually the amount of energy which is unavailable to do a work during a thermodynamic process. So that if we give this energy to any thermodynamic system, part of this energy is required to be used as entropy, which is to achieve the equilibrium temperature of that particular system. So we are losing some amount of energy to do a work. Therefore, our target is to have zero value of entropy. In order to have zero value of entropy, we are actually need a substance that is exists in the most perfect form of crystal, and the temperature of the crystal must be 0 Kelvin. If we can have that substance with that temperature, then only that condition we can have a zero entropy. In an actual condition, no object or system in this real world currently can have a thermometer or a temperature of a 0 Kelvin. So that a consequences of the third law is it is impossible for any process, no matter how idealized or no matter how perfect it is, to reduce the entropy of a system to its absolute zero value in a finite number of operations. The second law, in part, implies that heat can never spontaneously move from a colder body to a hotter body. So, as a system approaches absolute zero, it will eventually have to draw energy from whatever system nearby. So, if it draw the energy, it never can obtain absolute zero energy. So, this state is not physically possible, but it's just a mathematical limit of the universe. Therefore, the main use of the third law of thermodynamics is to serve as the theoretical limit where ideally the perfect system is when the entropy is zero. Thus, when we design or we calculate the performance of any thermodynamic system, we can know that the system is close to perfect system or not by calculating the value of entropy. The lowest value of entropy means the system is close to the perfect condition, and that is our target. So that is the third law of thermodynamics. Okay, we are actually finished studying about the law of thermodynamics. As a summary, there are four laws of thermodynamics, namely zero law, the first law, second law, and also the third law of thermodynamics. The zero law is used to define the temperature scale. Basically, majority of the temperature scale are similar. The difference is only the reference point that being used to define that particular scale. The first law is basically governed from the conservation of energy principle. Energy cannot be created nor destroyed. Hence, the total energy in this universe or in any thermodynamic system must always remain constant. Based on that, we have the mathematical equation of the first law, which is energy in minus energy out is equal to the change of energy in the system. As for the second law, we can define the direction of the heat flow, which is it must always flow from higher degree to a lower degree of energy in a natural condition. Also, we also can understand that the different substance will have different amount of heat energy. Finally, the second law will define the entropy of the system, which is the change of heat over the equilibrium temperature. Finally, we have the third law of thermodynamics. The third law of thermodynamics says that there is impossible for any thermodynamic system that exists in actual condition will have zero entropy. Thus, it will serve as a theoretical limit of any thermodynamic system to achieve. The lower the entropy, the closest the system to a perfect condition and should have a maximum efficiency. So that's all about the thermodynamic law. Alhamdulillah, thank to Allah. I have finished explaining to you about the thermodynamic and the law of thermodynamic. If you have any question regarding to this video, please ask it in our WhatsApp group or in our video conference later. Hopefully, this video will benefit your knowledge about the thermodynamic. So, the last word from me is, I will say that the good thing of this video is come from Allah Subhanahu Wa Taala, and the bad thing of this video is coming from my own weaknesses. With that, thank you very much and good luck in your study and in your life. Wassalamualaikum.